Okay, so I think we can start. So once again, good evening to everyone, and welcome to this new webinar. Now, as you know, this one is the first webinar regarding the new Python API that we have in STKO from version 2. So first of all, to follow this webinar, you need the latest STKO version, so version 2.0.1 actually. There is still some attending here. And to start this webinar, we already sent you some material and a video recording of a previous personal webinar that we gave to a university here in Italy. So if you have already had a look at that webinar, it will be easier for you to follow this first webinar. Okay, a few other attendees are coming. Okay, so we can start. I'm going to share my screen. Here we are. Okay, so I will very briefly introduce you to the new Python API that we have in STKO version 2. For more details, you can refer to the video that we already shared on our website, because it is going to give more details. And in particular, in this webinar, I will talk about how to use the Python API for customizing the post-processing in STKO and compute the drifts from the MPCO recorder, because as you will see, the drift recorder will not work with the parallel version of OpenSys, in particular with OpenSys SP. So in this first webinar, I will first give a brief review of the basic concepts of writing a Python code through a GUI. So I will just review a couple of the files that you can find in the folder called types. I will not talk about the preprocessor. We will do it in a future webinar. I will just give some concepts of how to access the output database for post-processing, and then I will apply this concept to the specific application of computing the drift ratios on a frame structure. If you have already downloaded the content files, here you will see that you have one Python file that was not complete. I mean this one, post-process drift plots. And if you look here, I gave it as an exercise for you to either to start trying to play with the Python API. And this is what we are going to do today. So basically, I will complete this webinar here. Okay, so from this point on. And I will show you how you can programmatically compute the drift ratios for all the columns in your model, how to automatically identify what are the columns in your model, and do an animated plot of all the drift ratios. Okay. So before starting with this, I want to give you some basic concepts. So first of all, if this is the first time you use STKO version 2.0.1, actually we released a new minor release here. If you don't have the script editor, it is just because it is not active by default. Okay, it should be like this. So if you don't see the script editor, you just can right click on the blank part of the toolbar here. Right click and you can open whatever you want. Okay, so script, and you have the script editor here. So let's see first how it works. The script editor is the same that you find here in the pre and in the post processor. Okay, so it is just moved between the two contexts. It is made of two main parts. The first part is the script explorer, that basically is a collection of folders where you have your own Python scripts. Okay, in such a way that STKO knows where to find them. Okay, and then the second part here is the script editor. So basically, what you want to do is to load here, pretty much as you do in MATLAB. Okay, when in MATLAB you have your own workspace, you can add folders, and once you add a folder, you can edit all the files that are in that folder, okay? So for this webinar, the only thing that you need to do, okay, we have other attendees. If you downloaded, the files that we share on our website, the first time you open this thing here, you don't have anything. So let me start from a blank settings. So the first time you open STKO, okay, and if it is the first time you use the script editor, this is what you will see, okay? So there is no path in the search path list, so we need to add some of them, okay? So for this webinar, you need to add the path where you have, in my case, it is in VB share, webinar Python share, okay? So you can add this folder here. Once you add this folder, you have access to all the subfolders that you can find there, okay? And then you can start playing with some of the files. Now, the first thing that I want to explain you is that, well, first of all, you need some good understanding of Python. And then there is something that I want to point out. That's why I created this folder called call types, because there is a basic difference between calling Python from a console application and from a GUI application. A GUI application is something like STKO, so it's an application with a user interface. What is the main difference? So if I go, for example, here in VB shared, and I go inside call types, okay? Now the basic function is call standard. Let's see how it looks like. Okay, it is a simple Python script. It just performs a loop 10 times and tries to simulate a very long operation. Okay, now here I don't have anything to do. I just use the sleep function from the time module to wait 0.5 seconds in each loop. Okay, this is just to simulate a long operation. Now, when I try to run this script directly from Python, so I'm going to open a PowerShell here, and I type Python call standard. As you can see now, at each iteration, it waits 0.5 seconds and writes the message that I'm writing within each loop, okay? And this is pretty simple, okay? This is what you expect. So every iteration, I do something that lasts 0.5 seconds, and then I write something. And in fact, you see the writing, you see the print here at each iteration, okay? There is no freezing of the GUI. This is fine because this actually is a console application, does not have a user interface. But the things are different if you call the same script from a user interface. Okay. Now let's see what happens if I call that script from my user interface here. So I clean the terminal, I open call standard, okay, same script as before. Now if I run this one, I expect to see this message every 0.5 seconds, but it will not work. Okay, I will see everything at the end. Okay, I play this, click on play, and I cannot actually interact with the application. As you can see, it is freezed. Okay? Then after 5 seconds, I see all the output at once. So why is this happening? I explained it in details in the video you have there, so I will go very fast here. This happens because when you have a GUI application, so an application with a user interface, the application is running on one thread of your computer, and that thread is already busy with the application event loop. Okay, so how does an application work? Well, basically, an application runs an infinite loop, which is called event loop, where basically the operating system sends information to the application, so the application can react to those information. For example, when I click with the mouse on my graphic window, the operating system is continuously saying to the application, someone clicked on this pixel, so do something, okay? And this event loop is actually making the main thread busy. That's why you don't see anything here. So when I run this script, the main event loop will block, and so you don't see no update from the GUI, and that's why you don't see any message here. So when the script finishes, you will see the output. Okay? So this is the first main difference. And of course, you don't want this to happen because the user that is trying to use your scripts, he doesn't know if your script is working or the application is crashing just because he cannot do anything. So every time you want to write a script from a GUI, you want it to be responsive in such a way that the user understands that there is a work in progress, but without freezing the GUI, okay? And there are many ways of doing it. Here I used all the kind of approaches. The easiest one is this one, okay? The easiest one is just to add an extra line here that says, okay, at every iteration, do something, and then tell the application to process all the pending events, okay? Now, this one is not very elegant, but does the job. Let's see. Okay, as you can see now, I'm seeing the information here, but the application is quite laggy, as you can see. Why? Because there is still one thread, and this thread now is in part busy with my loop, and in part it is processing events, okay? So at each time, my loop will be blocked by the application, and the application will be blocked by the loop, okay? So it will work, but it is not smooth. Then the nice way to do this is to use the working thread, so working with parallelism, okay? So you have one thread, which is the GUI thread, and then you run your lengthy operation into another thread, which is called the working thread. Now, in this case, I have many ways of doing it. If you want more details, you can go on my video tutorial that we shared on our website. There are 2 hours about these topics. And then I explain how to use a working thread, with GUI callbacks, how to use blocking threads, because I explained that using a working thread might be dangerous because the user can close the application while the second thread is still working. So at the end of the day, the easiest way of doing it is this function here, okay? Here there is an example. So the easiest way is to put your function, okay, inside a worker object, and then run this worker on a working thread, okay? So basically, this operation will just, let me show you, we'll just do the exact same thing, okay? But with a simple user interface here that does not allow me to exit or to do something with the application, so the application will not crash. But as you can see, it is not freezing, okay? So I see a responsive update of the application. Why? Because now I have 2 threads working. One is the GUI thread, and the other is the working thread, okay? So I suggest you to study all this topic in very detail because it is the basics of writing code in Python from a GUI, okay? So the first hour of the video recording that you found on the website is about this topic. Okay, then also in that webinar, I explained that with the Python API, you can actually also customize the preprocessor. Now there was a simple application here that draws some random geometry, okay? So for people that wants to perform parametric modeling, it can be done. It can be done directly inside the Python API, the script editor. So you can write vertices, you can create edges, you can do Boolean operations, you can add geometries to the document. And of course, you can do many more things. You can also create physical properties, element properties. You can do a lot of stuff here. So if you learn the Python API, and of course, you may say, okay, where do I find this documentation? You can go on help, about, and then you have the last link here, which is a reference manual for the Python API, okay? So if you click on there, you will find this kind of documentation. You have some examples, and then you have also documentation for each class, okay? And you can go here and you find the typical Python documentation for this. Okay, so this one was an example just to show you what you can do with the preprocessor. There is a nice example here for Gaussian random fields. I just want to show you the output of this thing. I don't want to talk about it, just to give you an idea. But here, what I had to do was to generate random material parameters, okay, to study the effect of material imperfections. And this example shows you how to use other libraries such as NumPy or Matplotlib and create some extra geometries directly inside STKO. So here you can actually draw your own things. Let me show you. In this example, I wanted to draw a cube, which is 200 times 200, and okay, something like this. And then I want to explode it so it becomes a shell. Then I go to the mesh tab. I make it structure and quad. Okay, assign done. And then I want to create a quite fine mesh. And I build a mesh here. Okay, now I switch off the visualization point just to show you the fine mesh here. And now if I run the script, it will basically create a random distribution of material properties. Okay, and this one is a matplotlib just to make sure that there is this effective random distribution. And as you can see, you can also have a visual representation of what you're doing. Okay, so you can use the 3D features of STKO to visualize your own stuff. And what I've done here is entirely by scripting. Okay, so I don't want to go into details. This one will be the topic for a new webinar. Just to show you that with the Python API, you can do a lot of stuff, starting from the preprocessor all the way to the postprocessor. Okay, so let me close this one. New document. Okay, and now I want to go directly to the post-processing. Okay, all the information that we need to start the drift example here are based on the basic examples that you can find in the post-processor. Okay, so 03 example post-processor. Here you can find some MPCO files. Let me show you in 03 post-processors. You find the output of two analyses that I've done. One is for response spectrum, and there is a script that allows you to create a CQC combination directly from the STKO postprocessor. And the other is the critical damage, which is basically the base for all these other scripts that explains you in the very basics of accessing an MPCO output database and get the data from the database. Okay, just to give you an example, if I open the critical damage, so I go in shared example postprocessor critical damage. This example is very simple. It is a beam, okay, a T-beam, but this is actually a beam. So if I switch off the beam exclusion, it is just a beam model. I want to remove this one, and I want to switch on the fiber color map. I switch off the grid, I switch off the beam exclusion, and I want to show you the damage variable. Okay, so this one is the distribution of damage. Okay, the damage variable is something that goes from 0 to 1. 0 means the material is fully linear. 1 means completely cracked. Okay, and so here the positive damage is saying where the material is cracked, and the negative damage is saying where the material is crashing. Okay, and you have the crashing here. In this example, I was basically showing people how to, if you can see here on the database, we can have a look at the element results that we have. And among them, we have the section fiber damage, which is the damage variable at each fiber section in the output database. Now, what you can do with the script, there are many things. Okay, so the first one that you can try is how to create a virtual result. Okay, if I open up this one, critical damage virtual result, this one basically explains you how to access the application, access the current document, okay, which is basically this one. Then from the document, you can get the database with ed equal to 1, which is this database here. Then from a database, you can get a result. A result can be nodal result or elemental result. Now, in this case, I want to create a result based on the damage. So I say, okay, let me get the damage. Okay, so database, get elemental result, damage, and this result will be stored here. Now, the next thing about this Python API is that now you are not bounded to the results that you already asked to OpenSys, okay? Because, for example, you finish the analysis, you ask some results, and the only thing that you can visualize in post-processing are them, okay? Now, with the Python API, you can actually compute extra results, like in this case. So the damage is a variable that goes from 0 to 1, but for some reason, I would like to have another kind of damage called critical damage, which is a sort of threshold, okay? So something that is equal to 1 for every damage index, which is larger than or equal to 0.9. 0.5 for every damage index that goes from 0.5 to 0.9, and 0 everywhere else, okay? So at the end, I will have 3 values, okay? 1, 0.5, and 0. So if I perform this operation, basically what I obtain is a result that was not available in the post-processor, but I can create it and I can add it back to the database as a virtual result. Why it is called virtual? Because it is not actually written anywhere, so it is in memory. It doesn't expand the database, so you don't have problem of space on your hard drive because it is computed on the fly. All you need to do is to tell STKO how to compute it, and STKO will compute it on the fly every time you try to plot this result. Okay, so if I try to run this one, you will see that a new result will appear down here, and the name will be critical damage. Okay, so just to explain you what happens here, D is a result. Okay, so contains all the results over all these points. D larger than or equal to 0.9 will give a Boolean matrix made of ones or zeros. Okay, ones for every entry of D that was larger than this one, 0 for everyone else. And these values for me are the critical damage, so the largest one, so I want to see a 1 for them. And then I want to see a value of 0.5 for every value that goes from 0.5 to 0.9. So I can do this first Boolean matrix, then this other Boolean matrix, then I perform an AND operator, so I keep only the values that are true at both sides, okay? And then this one will be a Boolean matrix once again, so made of ones and zeros, and I scale it by 0.5. So at the end of the day, what I obtain is this one. So I run it, I have another result. As you can see, it is immediate. It doesn't take any time because it is not the real result. It is called virtual just for this reason. I'm just saying STKO how this result behaves, okay? But I will never write this result on the database, okay? So don't worry about memory usage or space on the hard drive. There is no problem. Okay, so once you have your virtual result here, you can go on the editor. You click on the fiber color map and you can change from the original result to the virtual result, okay? And now, as you can see, I have just 3 values. 1 for every value that was larger than 0.9, 0.5 in the middle, and 0 everywhere else, okay? And here you see the 2 levels of how I decided to code them. Now, just to show you that this is something that goes on the fly, I can give it another name like critical damage 222. Here I can call positive damage, and here I can give some other random name. Okay, if I run this one again, I have another result. I go back here, I go in the editor, I change the result, and I have positive damage or CCC. Okay, so it is completely computed on the fly. So also here, I don't want to go into details. If you look at this this example, it will give you the details of how to access the application, which is in the MPCO module, how to get the document, how to get the database, how to get the real result from the database, and how to compute a new result. Okay? And finally, how to add it back to the database for post-processing. Okay? So this one is one of the main reasons you can use Python API on post-processing. I think we have a question here. Is it possible to create a surface color map result from a fiber result like this one? For surface color map, what do you mean? You mean a solid color map like this? So the surface color map based on the fiber. Okay, we have first question. Actually, you can. It is quite complicated to explain now, so I will prepare a new webinar on this. But there is a way to convert a result on fibers on a result on Gauss point, and from Gauss point to nodal results. Okay, so it will be possible. It is not so basic, so I will cover this topic in a new webinar. Okay, and from UA1, what is the function of pi side 2? Okay, pi side 2. What is the story about pi side 2? In STKO, we use the C++ library called Qt. Okay, and Qt is the library that we use for the user interface. Okay, that is a C++ library. But then the Qt company decided to create a Python interface for the Qt library. At the beginning, this library was called PySide2. Now it is called Qt for Python, but it's the same way. So this one is the Python interface for the Qt library. You need to use this one because STKO uses Qt. Okay, so you cannot use another GUI library, otherwise it will be in conflict with STKO. That's why every time you need this one only when you want to create user interface. Okay, so let me show you. You mean all these things here. As you can see, there is Qt, QObject, signal slots, Qthread. This one has all to do with UI. So if you don't want to create any UI, you don't need it. Okay. But of course, if you want to create some interaction with the user interface, you need PySide. And if you want to understand how PySide works, well, it will take a lot of time for you because Qt library is a very large library, several thousand of classes, so it will not be easy to learn it. But if you want, you can learn it from either from the C++ code or from the PySide2 manual. It is just a matter of time, but you really need it only if you want to create user interfaces. I think we have another question. Okay. I think the best way actually to learn a library such as PySide, which is, as I said, Qt, is not to start directly from the Qt library because it is very large, so you don't know where to start. For you that you are not software developers, so you're not really interested in learning the entire Qt, probably the easiest way is to look at these examples and try to understand only the basic functionalities that you need. Okay, so for example, as I did here, how to create a progress bar, how to create a dialog. Okay, but learning the entire Qt library will take a lot of time. Okay, so this one was an example on how to create a new result. Okay, but then you are not limited to get a result, modify the result, and add it back here, because this is fine for graphical post-processing. Okay, like this. But sometimes you may want to do extra things. Okay, so you don't want just to look at the result from a plot. Okay, you actually want to interact with the database. So you want to get the result, you want to create plots, you may want to create reports. Okay, so you want to do whatever you can do with a database. Now the MPCO database is a binary database, so there are actually two ways to understand what is inside. Let me see, we have other people here. Okay. The MPCO database, and I'm going to show you how it looks like. For example, this one. You cannot visualize it from a text file because it is a binary file. So if I try to open it with a text file, all you see is that it is an HDF5 database, but it is binary. Okay, so you cannot see what's inside from a text file. What you can do is to either install HDFview, which is a Java-based application that allows you to go inside an HDF5 database. And remember, MPCO files, even if the extension is MPCO, it is actually an HDF5 database. Okay. So, for example, if you want to see what's inside this thing here, you can drag and drop it directly inside the HDF5 view application, and you can see how the MPCO database is structured. Okay. So you can see what is a model stage, what we have in the model. As you can see here, we save the nodes, coordinates, IDs, and then you have all these data sets. Okay. Either about the model itself, sections, fiber sections. Here you have all the information that you need, but also results, okay? So you have results on nodes, results on elements, and so on. What's the problem is that you don't really understand how to read the data from this database, okay? So for example, you don't know what is the Gauss IDs or what is the multiplicity. So it can be very difficult to try to understand what's inside the database just by looking at the data sets. That's why we decided to create this Python API, because here it will be very easy to access the database in a programmatic way and get data from it, okay? So this one is just a way to get a result and create another one. But actually you can also query result along the mesh, okay? So for example, here we have 4 basic examples, okay? So how to query result on nodes, how to do the same on Gauss point, or on element nodes, or on element fibers, okay? So for example, let's say I want to access the data from a given result onto a precise node, okay? So let's say, for example, I want to create a chart of the displacement history of the top node here, okay? Now you may say, okay, well, I get the application. Well, here we have some stuff to create a graph. This is not necessary, okay? I just want to create an animated graph, okay? So if you want to do this, you can follow this approach. This is how to do it with Matplotlib embedded into a cute GUI. But the real point is here, okay? So I get the application, I get the document, I get the database. Then I know that in this model I have 2 stages, okay? Graphical analysis and cyclic pushover analysis. So the second stage is the stage that I want, okay, the last stage. Then I want to extract a graph for all the steps of the second stage, okay? So I get all the steps here, and I prepare something that is called evaluation option. That is basically a container of information that I will use to extract data, okay? Then I create my dialog just for visualization. This is just stuff for the creation of a plot. Then I have my working thread. As I said, all the examples that I will share will use working threads, otherwise the GUI will freeze. And what do I do inside this function? Well, the first thing that I do is to get another result. Here I want to plot the displacement history. Okay, so I get a nodal result that contains the keyword displacement. So basically it will give me this result here. And then the problem, how do I access the data inside a result? Okay, so you don't know how the data is stored inside the MPCO database. That's why we created some utilities, like, for example, if you want to know what is the row associated with a particular node, you can use this function. So MPCO ODB result field dot node, and then here you give the nodal ID. I know that the node here on top has the tag of 3. So this function here will give me a class that is the row identifier of that node. So you don't have to worry about how the database is structured. You can simply say, okay, give me what is the row identifier of this node, okay? Then the column instead is an index, okay? And it's up to you. For example, here I know that the displacement field has 3 components, UX, UY, and UZ. And so the column is a 0-based index. Now in this case, I want the displacement in the Y direction, so I say that the column is equal to 1. Okay, then I do some stuff to compute also the envelope, but this is not important. So for all step, I go to the evaluation option, I update the current step, and then I tell the result to evaluate the result field at this stage and this step. Okay. So this function here will give me what is called a result field. It's kind of a matrix. It's not really a matrix, but it's similar to a matrix. Okay. So once you have the row identifier of your object and the column, which is the component of the result that you want, you can simply say field. Then you access with the row and column accessors, and you get a scalar here, which is the result of node number 3 at component 1. Okay, which is actually the second component. Then once I have this one, I append it to my list of results, and I do some stuff to compute the historical maximum. Okay, and then I run everything on a working thread. Now I run this application here, and what you will see is an animation of the displacement history on top and its historical maximum. Okay. Now the key point here is not actually how to animate a plot, because this is a graphical stuff. It's not related to STKO, but it is this point here. So how to get a result, how to create the row and column accessors. Okay, but the most important is the row one, because the column, as I said, is an index. Okay, but the row is not actually an index. Why? Because the field here is not a matrix. It is a special class. Okay, that given this component and given this accessor, it will give me the result of that node. So how do the same with Gauss points? Well, it's pretty easy. Okay, you can see all this file, which is basically very similar to the previous one. The only difference is that in this case I want to plot, for example, on a Gauss point, I want to plot the moment curvature at the Gauss point at the bottom here. Okay, so the only difference is that now I get two results: section deformations and section forces. And of course, they are elemental results because they are stored on elements. So I get two of them. The column, once again, is an index, okay? And it is equal to 2 because my and moment about the y-axis and curvature about the y-axis are actually the third component of the force vector of this kind of beam, okay? So that's why 2. Remember, the column is 0 based, okay? And the row, how do I compute the row? Well, pretty much as I did before, but instead of using the node function, I use the Gauss function. The Gauss function takes two arguments. The first one is the element index, okay? So the element ID, and this one is the first element. It has an index equal to 1, but it can have any index. And then you have the Gauss index. I want to plot it on the bottommost Gauss point, so I put 0 here. Once I have this accessor, I can do a loop on all the steps. I evaluate the field in X from the result in X, and I evaluate the field in Y from the result in Y, and then I get the data, okay, with my row and my column. And I get a scalar here, which is the curvature, and this one is the moment, okay? Then I append it, I compute the positive and negative envelope, but once again, this is not necessary. And so the output will be something like this, okay? So an animation of your moment curvature response, a positive envelope, a negative envelope. This is not necessary, but it was just to play with the data, okay? And of course, you can do the same with fibers. So remember, now I was focusing on the row accessor, okay? So before it was a node. So here you have how you get the data from a node. MPCO result field node with the node index. For a Gauss point, it is the same, but with two parameters, element and Gauss. And so for fibers, it will be the same, okay? But it will take 3 parameters. So let's go down here. You have fiber, okay? And it takes the element ID, the Gauss ID, and the fiber ID, because remember that fibers are stored inside a Gauss point that are stored inside an element. Okay, that's why you need 3 arguments. And then, of course, here I need different results. So fiber uniaxial strains and fiber uniaxial stresses. And then the rest of the script is exactly identical to the previous ones. Okay, so I run this one and I see the stress-strain relationship of the topmost fibers down here. Okay. So basically here, if you ever look at all these files, you will learn how to access a database, okay? So remember this one, critical damage virtual result and response spectrum virtual result, basically explains you how to create a new result, while all these files here, the query files, explains you how to access the data and do some post-processing, okay? Now, in my case, I was printing them on a matplotlib plot, but you can do whatever you want. You can actually create a file, create a report, so you can do whatever you want. We have another question. sorry, do we need to put worker thread files in a certain folder? This is not necessary. When it comes to programming, it's up to you. You can decide where to place your files. Typically, when you do your programming and the same operation are repeated over and over again, it is useful to put them in a util function. That's why this is exactly what I did when I was explaining the call types. Now, just to explain you this concept. When I was talking about the standard call here that was not working, then I explained in the video that I sent you how to use, for example, the blocking working thread. If you see here, I do a lot of stuff. I create the queue blocking slot, I create a function to run something on a working thread, then a worker dialog, all this stuff. Instead of repeating them over and over again, okay, or how to set up a thread, how to set up a worker, how to tell the thread to stop the worker, and vice versa. So instead of repeating these things over and over again, I decided to put them in a function called thread utils, okay? So here I have all my components that will be called in every script. And then in every script, for example, this one, the final one, which is the one that you will be using, instead of creating once again all the worker dialog, worker thread and stuff, I simply include the thread utils, and then I just need to put my function inside a simple worker, define the signals, and then I call tu run on worker thread. Okay, so you can put it in whatever folder you want. The only point is that you need to, this folder needs to be in one of the folders that you have here. So when you run a script, your script can find that library. Okay. But this is all about Python and about coding. It's just a matter of coding style. So you can do whatever you want. You can repeat that code over and over again, which is not the smart solution. Or take that piece of code that you use very often and you put it in a utility class, okay? And this is exactly what I did here. Is it fine? Okay. Okay, so let's go on. Okay. Okay, so once you get all the basics, so how to do the call type, so how to work with the working thread, how to understand how to access the postprocessor and get data from the database, you can actually create some complete automations. Like in the example that I'm going to show you now, let me create a new document here, is about the drift recorder. Now, I don't know how many of you have used the drift recorder, probably a lot, because it's something that is quite used in OpenSys, and it works. The only problem that I found is that when you have a large model and you want to run it with parallel processing, so either OpenSys MP or OpenSys SP, the drift recorder will not work because it has not been implemented to work in parallel processing, okay? And so this is a problem because if you have a very large model and you want to run it in parallel, you cannot use the drift recorder. So how do you create the drifts once your analysis are done? Okay, and in this example, I will show you how to replicate exactly the drift recorder of OpenSys from the STKO postprocessor. Okay, and finally, how to do an animation of a drift plot. Okay, so just to show you how to understand this thing here, you can go directly inside the folder drift OpenSys SP. Okay, here you have two files, two STKO files, which are basically the same. They only change in one small option in such a way that the drift file is called drift for the one processor test and drift SP for the multiprocessor test. Okay. But for the rest, they are the same. And this one, we produce this output here. So just one output database. And the parallel one, we produce 4 output database. Okay. Now let's see what happens. I will first go into the preprocessor and open. So don't worry, that model is very small, so it's quite easy to run all of them. So webinar Python share drift OpenSys SP, and you open the test number 1. Okay, so this test is made for running with OpenSysSP, but using just one processor. So let me make sure I'm using OpenSysSP, yes? Because as I said, the drift recorder is not, actually I made a mistake. I said that it doesn't work with OpenSysSP. Actually, it works with OpenSysSP, but only if you use one processor. Okay? If you use more than one processor, it will not work. So you can go here, you can look at the file, it is not important, but what is important actually is down here, how I define the drift recorder, okay? Now you know that in STKO we don't have the drift recorder, we only have the MPCO recorder, but whenever you want to write something that is not available in STKO, you can actually put a piece of TCL file here, okay? So as you would usually do with OpenSys. So here I'm creating a drift recorder for 8 columns totally, okay? So I have basically a drift recorder for one column here, which are actually 4 elements, and another column here. Why I took 2 of them? Because I know that one of these will fall inside one processor and this other in another one. So I made it in such a way that it will not work with OpenSysSP. Now, if I run this one is for the single processor. As you can see, the name of the file will be drift, drift.txt. Oh, and let me remove these files so you can see them from the very beginning. Cancel. Okay, so if I run this one, it will work, okay? So OpenSysSP, but, oops, let me just put one processor and run it. Inside drift OpenSysSP, that's fine. Okay, as you can see, there is no warning here because it is OpenSysSP, but with just one processor. So there is no complaint about OpenSys, about the drift recorder. So you wait for the analysis to finish. Okay, that's fine, no error. And this analysis will produce the result file and the drift file. As you can see here, we have 8 columns. Why 8 columns? Because we have 4 elements for each column that I recorded. So 8 drifts for each time step. Okay, so we can close it. And now I try to do the same, but with OpenSysSP. Now imagine this model was a very large model, so you needed actually a parallel processing. So I open the other one, which is OpenSys test for processors. As I said, the file is exactly the same. The only change I made is on the drift recorders, because instead of calling it drift, I call it drift sp.txt. Why? Just because I want to compare them and show the differences. Okay. So if I go here, I say for processors, OpenSysSP, run it. Now it will be much faster, but you will see some differences now. Okay, now it will be, of course, much faster because I'm using 4 processors. And at a certain point, you may see some crash. Here it didn't crash, but it will crash at the end, as you can see here. Now let's see what happened. At the very beginning, it was saying here, right after creating the drift recorder send self should not be used in OpenSysSP. Now this method here is a method used by OpenSysSP when you have more than one processor to send data from one process to the other. Okay, and basically the drift recorder said, okay, you cannot use a drift recorder in OpenSysSP. Now it is fine because the analysis keeps on going. Okay, the problem is that this warning may happen that you don't see because you're just looking at all the output and you forget to see all the warnings. But then when you go at the end, it created a crash here, as you can see from this output. Because actually it is bugged in OpenSysSP, the drift recorder. So you go at the end and you have a crash here. Now this analysis is very short, so the crash happened at the end. But if you're doing a larger analysis, it may happen that the crash happens during the analysis, okay? So I'm going to close this one and let's see the output. If you go here, you will see that an output has been created. So you say, okay, but he said that it was not working with OpenSysSP, why do I have an output here? Well, first of all, you can see the size. It is half the original one. And if I compare them, and I use something called WinMerge to compare them, you will see that the first one, drift, has 8 columns, and the other one only 4 columns. Now, the first 4 columns are exactly equal. So basically, what it is saying is that this drift recorder has worked, but only on the first processor. Okay, it was not working on the second processor. So this is a problem. This is a problem when you need to record drifts on a very large model. And the nice thing is that using the Python API inside STKO, you can actually simulate what OpenSys would have done with a standard recorder. What are the advantages? Well, first, that you don't need to write a lot of files. You just need the MPCO file. And from this file, you can extract data and compute all the results that you want in post-processing. Okay, so even if you forgot to use a recorder or a certain recorder doesn't work with your OpenSys version, you can simulate the same thing in post-processing. So I try to do this one. So if you go inside, well, first of all, you need to go in post-processing. You need to open the, what is it, 04 drift OpenSys. You need to open the partition database, okay, because I want to show you that with the results of the parallel analysis, you can get the same drift that you had with the sequential analysis. So you can open just one of them. STKO will take care of open the other 3. Okay, and here is the output. Let's see, first of all, what is going on. You in the editor, I increase the deformation scale. Okay, so here I was also using rotational transformation. So I have the soft story here, and then a small torque due to the presence of the staircase here. Okay, so when I will see the drift, I expect to see an increasing graph down here. So once I have this one, I can go in the script, and I can run a script that you already have, which is the drift recorders. Okay, post-process drift recorders or post-process drift recorders working thread. Okay, these are 2 examples of how to write the same thing sequentially or with a working thread. Now, of course, I will explain you how to do it with the working thread. Now, in this example, I want to replicate exactly what I did with my drift recorder in the sequential OpenSys version. Okay, so how you can do that? Well, you create the worker as usual. And then you get the document, you get the database, then you decide, you open a file for writing, and this file will be called drift sp stko, just not to overlap with this one, okay? So then do a comparison. Now the drift target I and j, they are the tags of the nodes, which are the same that I used here, basically, okay? Nodes I are the nodes at the bottom of the elements, and j at the top. Okay. Perpendicular direction is 3 because I want to compute the drift along the x-axis. Okay, so dot1. Close this one. Post-processing. So I copy. I need 2 lists of the I nodes and j nodes. Then for computing the drift, I need the displacement. So I go to the database. I get another result displacement. Then I want to compute the drift only for the second stage. So I get all the stages, I get the last stage, and I get all the steps and all the times of the last stage, because that is the pushover analysis, okay? And then I initialize the evaluation options, I set the stage, and then I will set the step later on, okay? Then I say, okay, now I want to evaluate the displacement at each step, so that at each step I can compute the drift, okay? So I get the number of steps, and I say for step counter in range number of steps, I get the current step ID, and I get the current step time, and I just want to print something, okay? I am evaluating the results at step ID, and time equal to step time. This is just to give an information to the user, and it will appear down here. And then also I want to use the progress bar of my dialog to show the user the progress of my operation, okay? So it would be the step counter plus 1 divided by the total number of steps times 100 because the percentage should be given from 0 to 100, like an integer, okay? Then I sleep for 0.05 seconds just because this operation is very fast, okay? But I want to show you how it happens inside the dialog. So I'm just simulating a very large operation, okay? So I make it sleep 0.05 seconds. Then I put the current step ID inside the evaluation option, and finally I can evaluate the result. Okay, so displacement evaluate at the current step, and the output of the evaluation will be the result field. Okay, so I call it displacement field. Now I need to compute the drifts. Okay, so for computing the drifts, I don't only need the displacement, but I also need to access the position of the mesh. Okay. So you may say, how do I get the position of a node from a database? Well, in the MPCO database, as I've shown before, we do not only save the results themselves, but we also save data about the mesh, okay? In such a way that we can get mesh information later on, okay? So for example, for each time step, I want to save one row with 8 numbers, which are the drifts of the 8 columns. So I pre-allocate a vector here, which is empty at the beginning. And then I say for each node in the number of nodes that I'm trying to monitor, I get the index of the I node and of the J node, so bottom and top node. I need to get the row accessor inside my field. So as I did in the previous example, once I have the nodal tag, I can get the row from the MPCO or DB result field node index and node index here. So here I have the row accessor for I and J. Once I have the row accessor, I can simply go inside the displacement field and use the row index and column index. Now, as I said, I want to evaluate the drift along the x-axis, so I use 0. If you want to do the same for y, you can use 1. So in this way, I get the displacement in x at node I and node j. Now I need to get the position of the 2 nodes along the z-axis. So how can you do that? Well, always using the field that you just evaluated. But instead of getting the data, like this, you can get the mesh. And from the mesh, you can get the node, or you can get also many other things. But in this case, we only need the node. So mesh, get node with a certain tag. This one will give me a node object. The node object has one attribute called position, which is the position in space. And the position has 3 components, x, y, z. Okay? So in this way, I get the z component of a node of my mesh. And then I can get the position about the z-axis for node I and node j. Now the drift recorder computes then the absolute value of the distance, so the total height of my column, and then the drift will be top displacement minus bottom displacement divided by the total length of my element. Okay, so this one is actually a drift ratio. And then I append this one to my list of drifts using the same format that I asked for in OpenSys. As you can see here in TCOL, I was using, if I remember properly, a precision of 3, okay? And just to show you an exact comparison, because if you use different precisions, of course, you will see small differences, okay? But those small differences will just be due to round-off errors. So here I use a small precision, so both of them will give me the same round-off error, okay? And so I append everything at this time step here, and then I write everything in my file, okay? And then next line, perfect. If you run this one, and you run it on a working thread, it will create a file here called drift.sp STKO. Now you run it, okay? Now it is taking time just because I put the sleep here, because actually this operation is quite fast. If I comment it out here, and let me clean this up, the operation is quite fast, and the dialog doesn't even appear. Okay, so I put this. Okay, I put this one just to make it more funny. Okay. I think we have a question. In the displacement object, will the length of the element change? No. The length is the length of the mesh in the undeformed configuration, okay? So if you want to know what is the deformed configuration, you can just add the total displacement, okay? So this one mesh is the initial mesh, okay? So it will not change. Does it use the initial position or current position? Exactly as this question. It uses the initial position, okay? So the exact position that you put in OpenSys. If you want to get the current position, so the deformed configuration, for example, if you're doing large displacement analysis, you can simply get the total displacement, like this, for example. Here I'm getting just the just one row, just one scalar, because I asked for row and column. If you want the total displacement, like EU is equal to displacement field, and you put just the row, okay? If you put just the row, it will give you the entire row, which are 3 components, X, Y, Z, and then you can compute this deformed configuration as this one plus EU2, which is the Z component of this vector. So here you have the Z component of the deformed configuration, okay? So it's up to you if you want the deformed or undeformed configuration. Now, since we are working in small displacements, I don't need the deformed configuration, okay? That's fine. Okay, so the analysis has been done. I go back here and I have drift SP STKO. Now you may say, okay, but there is something different. We will see it actually. I take the first one and the second one. So the sequential, which was the working one with menu 1, and I click on win merge, and you will see that there is no difference. Okay, so the exact same numbers from top to bottom. Okay, so this is a way to replicate the drift recorder directly inside STKO. So you may ask, but why this one is 7 kilobytes and this one is 6 kilobytes? This is just about some convention in writing the code. This one has been written by OpenSys, and OpenSys only puts here the line feeding. You know, for going to the next line, different operating system use different characters. So if you want to know what is the character for the next line, you can go in view and sorry, this is Italian, I will translate it for you, but show symbols for line ending. So OpenSys is using the line feed. The line feed character is actually the \n character, which is used to go on the next line. While Windows, so here, since I run this one on Windows, on Python directly translates this one, the end line, with the Windows end line, which is the carriage return plus the line feed. And let's see what I mean here. If I open this one, okay, so you have CR, LF. These one are actually 2 invisible characters. One is for the carriage return and one is for line feeding. Okay, it's just a matter of differences between Linux, Windows, or iOS. So it's not important. That's why you may see some differences in the size. Will the webinar material be shared for practice? Yes, actually, as I said, probably you just entered, not at the beginning of the webinar, but we already shared all these files and they are on our website, and more precisely here, let me go as they are soft. If you go on products, training, and you go on our webinars, e-learning courses, okay, so here you already have the contents of actually, yeah, here if you go on join e-learning and you go down here, you should already have, yeah, download files. Okay, so you can just download here now the files, and you have all the files that I'm working on plus a 2-hour video of a previous webinar that we gave to a university here in Italy that explain all the details of what I'm doing today. Then today I will change a file because there I gave you an exercise to complete, and I will share the new one and this video on by tomorrow. Okay, so you will have an updated version of these files tomorrow. Okay. So as I said, the only difference is about the end line character, so nothing important. That's why you see only a small difference here, but the content of the file is exactly the same. Okay, so up to here is fine. You understand the how useful it can be to have a Python API for accessing a database and doing whatever you want, basically. Okay, this one is a very simple example, but all the next webinars will be focusing on this topic. Okay, you can do something more. I prepared an example, which is a mix of this way of getting the data, okay, but also how to create an interactive plot showing the drifts in real time. Okay. So one thing that people may say is that, okay, this is nice, it's very useful, but I need to know the IDs of my nodes. Okay. So if you know them, it's fine, but how do I do it in a programmatic way? For example, this script can be used with this model, but if I use the same script with another model, it will not work because I need to change the ID of my columns, okay? And this is quite annoying because you don't want to repeat this operation over and over again. So I prepared another file here, which is called drift plot. The one that you have is called drift plot. Here I renamed it drift plot trial, and this one is the complete one. But if you open this one, so the drift plot, you will see that now I have a plot canvas just because I wanted to prepare the file for you. So here, this one is used to create a matplotlib plot, and it is empty at the beginning. So a dialog that will freeze the user so that the user cannot interact with the application until the worker thread has finished. And then I have my worker class, okay? Here I do the same thing I did before. So I get the document, I get the database, I get the displacement field, I get all the things that I need for doing the loop on the last stage because it is the pushover stage. And then I do something. Here I showed you how you can use the mesh, which is inside the result field, to identify what are the columns in a programmatic way. Okay, so how I did it? Well, I evaluate the displacement field at the first step. Okay, this is not important which step you use because I just want to access the mesh. Okay, it is not important the step in particular. So I get the mesh, and here what I want to construct is a dictionary whose key is the XY coordinate of a column sequence here, and the associated value is a list of columns. Okay, well, actually it's not only a list of columns, but this column here will contain n tuples, where each tuple has the z coordinate and a pointer to the element in my mesh. Okay, so here, for example, for this column here, I will have a list containing the z of the middle of the column and the first column, then the z of the second column and the second column, third and fourth. Okay, and this one for each xy coordinate. Okay, so it is a simple structure to identify all the columns. And for me, a column is something that is oriented about the z-axis. Okay, so this script will work for every structure whose columns are vertical, basically. Okay, let's see how I did it. First, I created a class called xy_key. So you may say, okay, but why didn't you use just a tuple? Well, because there are round-off errors. So when I want to perform comparison on floating numbers, I need to use some tolerance. Okay, I cannot just say that x is equal to other x, because there can be a very small round-off errors that does not result in equality. Okay, that's why I say if the absolute of the difference is less than a tolerance, then for me is equal. So this one is a simple structure used to compare a pair of floats. Okay, then I create an empty dictionary and I say for every element, id an element in my mesh elements, because this one also is a dictionary of id and elements. If the elements has two nodes, because I want to restrict the usage of the script only to two-noded members, so beams or trusses. Okay, then I get the orientation, so the local axis of the element. How can you do that? Well, element orientation, this one gives you the local axis. Compute orientation, this one gives you a 3x3 matrix, orientation matrix, and the first column is the x-axis, okay, so the axial direction of the column. If this x-axis is aligned with the positive or negative z-axis, so keep in mind that this one is normalized, so I just need to check if the third component is close to 1, either plus or minus 1. If this is true, it is a vertical member, so for me it is a column. Then I compute the center, I compute the x and y of the center, and I use this one as a key. And then I put this element into this column list. So at the end of this list, I have a structure called a structure that basically gives me all the columns, okay? So if I run this application here, I just print it, okay? And then here I left it blank for you to complete it. And I will show you the complete version. So if I run this one, as you can see, I prepared the plot, but the plot is not doing anything. I can simply close it. And here you can see the output of all my columns, okay? Just to show you what this map is actually. Okay, so I identified 23 columns, okay? And in fact, I have 23 column sequences here, each one made of 4 elements, and some of them had 5 elements, the one in the middle, okay? Because there is this extra part of the roof. And they are ordered by the z coordinate, okay? Starting from the bottom, going to the top. Okay, so this simple structure is very useful to identify the columns in your structure. Okay, so it would be nice to complete it doing a loop on all the time steps, getting the drift ratios for each one of these elements, grouped by column, and then plot all of them into the into this one basically. What I would like to do is to compute the drift ratios for every column, for every element in every column. For me, this column means a column sequence. And in the ordinates, so in the y-axis, I want the z coordinate of my mesh, and in the y-axis, I want the drift ratio. Okay, so let's close it, and I will show you the complete one. Now I don't have time to write it on the fly, but I will show you all the pieces. So if you open the drift plot that I will send you tomorrow, okay, so the complete one, it is exactly the same file. The only change are, I needed to add an event loop here. I need to include an event loop because I need it later on in my plot. Then I did some small change here. Okay, so after my, okay, here. Now what I need to do is to extract my data. So the first thing that I've done was to create a simple function that takes one element and orders its nodes to make sure that the element is oriented along the positive z-axis. Why? Because I order all the elements inside this column map according to the center of the element, okay? So this element will come first before this element before the other, but I'm not sure if this element is oriented upward or downward, okay? And to compute a plot of the drift, I need to make sure that the first node is the bottom one and the second node is the top one, okay? So this simple function is just taking the ID of the first two nodes, the z coordinate of the first two nodes. Then if the second coordinate is less than the first one, I do a swap, okay? So I swap the z coordinates, I swap the nodal IDs, and then I return a tuple with the nodal IDs and z coordinate eventually swapped, okay? So I put this one here because I will need it at least twice. That's why I put this code into a utility function. Keep in mind that in Python you can write a utility function inside another function. It's perfectly fine. Okay, so now I need to create some plots. Okay, so some data for matplotlib, and I need an X and Y array here, X and Y list actually, one for each column. So I need to create another map, another dictionary, and I call it plot column map, which have the same keys of my column map before, but the value will be a tuple of X and Y vectors so that I can use them to update the plot in matplotlib, okay? So pretty much as I did before, I can say for each item in my column dictionary, okay, so the key and the column list, I compute the number of elements given by the number of entities I have in column list, and then I pre-allocate two vectors at the beginning made of zeros, and this one should be large, 2 times the number of elements, because every element has 2 nodes, and I need a drift value for each one of them, plus 2, well, just because, let me do a drawing. Imagine I have 2 elements here, so 1 and 2. My plot needs 2 values for the first drift, okay, so this one, then 2 values for the other, so this one, and this one will be my plot, and then I need a first value that will be always 0, and the last value that will be always 0 at the Z location, okay, so that I can close my loop, just for that, okay. So that's why I have 2 times number of elements plus 2. Then I loop through all the elements, I get the current element in this column, I make sure that the ID and Z coordinate are ordered from bottom to top. And then I write the, I fill the Y vector, because the Y vector contains the Z coordinate, so it does not change during the analysis. So that's why I pre-compute it. But at the beginning, the X axis will be always 0. Then I need to perform a loop over the time steps to fill the x-axis, okay? So at every time step, I get the drift ratios, as I shown before, for every element in my column, and I get the x and y data, and I update the x using the drift function that I used before, okay? So pretty simple, but instead of writing the drift onto a file, I put the drift inside the correct location of the x-axis, okay? So once I do this one for all the columns at the current time step, I update my canvas. Okay, so my figure will update and will show me the drift at the current step. Okay, so all the drift overlap. This one basically will create an animation of the drifts that are changing during the analysis. Okay, so let me run this one. Oh, another thing that I made, another change that I made, is that if you look at the previous file, if you look at the original one, let me show you, which is plot trial. If you look at this one, I added one function in my dialog, okay? So my dialog has an accept function and the OK button, which is the OK at the bottom. When it is clicked, it calls this function here, on click. And on click allows me to accept the dialog, and so the dialog will close. Now, what's the problem? Here there is no problem actually, because the function is so fast that my working thread has already finished. So once I click my close button, it is perfectly fine. But what happens if I do it while there is a working thread? Okay, so let me show you. But first I need to save it because I will crash my application now. I will show you something that is very important, otherwise you will crash STKO many times. Now, I want to crash it on purpose, so let me save something. Okay. So if I don't use this one, which is basically this function here, I made the OK button disabled at the beginning, okay? So if I don't use this one, and I don't use the allow close, okay, so it is not important, I can, okay, comment this one. If I run this, okay, it is fine, as you can see, it creates an animation of the drifts, and now I can close it. So you can say, now this is perfectly fine, nothing is happening. But what happens if I click the OK button while it is going? I click it, and my application will crash. It should crash now, perfect. Why is this happening? Because actually I closed my working dialog, okay, while the working thread was still going, okay. Actually, the working dialog is meant to stay alive until the working thread finishes, okay. That's why when you use the working thread approach, study very well the call types because you need some concepts, otherwise your application will crash over and over again, okay. So what I did is simply to, let me reload this one so I will show you what I did, was to say, okay, I don't want the user to click on the OK button from the very beginning. So I added this line here that say, okay, once I created the OK button, by default, I set it to disabled, okay? So set enabled false, it means that it will appear grayed out so that the user cannot click on it, okay? But this is not enough because if the user cannot click on it, it will never call the click signal and it will never close my dialog. Okay, so it will be open forever. So I need a point in which I can close it. So I created a function called allow close, and this function is a slot. When you study Qt, you will learn what is a slot, what is a signal. And when the allow close is clicked, it will set the OK button enabled. Okay. So when the OK button is enabled, the user can click it and can call the accept function of the dialog. So when do I call this allow close? Well, actually when my worker thread is finished, but not here. When you work with Qt, you need to learn the signal and slot mechanisms, which is very nice. So here I do my operation, okay? When my operation finishes, the thread emits a signal called the finished signal, so that when this signal is emitted, I know that the thread has finished. So I create the worker here, and I say, okay, I want to connect the worker finished signal to the dialog allow close slot, so that, and then finally I run the thread, okay? So I run the thread here, but when the thread will finish, it will emit the finished signal, and the finished signal will call the allow close that will make my OK button enabled, okay? So if I run this one, as you can see now, I cannot click on close because it is blocked, and only when the thread finishes, my close button is enabled, so I can safely close it, okay? So these topics are very important because otherwise you will never be able to start coding with a GUI or coding seriously using working thread, because otherwise you will always create very simple applications and they will be buggy. Okay, so learn quite well how to do these operations. And of course now here I was computing the X drift, so the drift about the X-axis. Let's say I want to compute the drift about the y-axis, and y-axis, since I have torsion, I will see drifts in both sides. I can simply go here. How can you do that? Well, I go where I compute the drifts, which is down here, and I simply need to change the column. So instead of 0, I put 1, and I can see the drift on the y-axis. Okay, so as an exercise, for example, you can take this script, evaluate the drift both in x and y, and create 2 plots instead of 1, for example. So if I run this one, I will see, okay, so the drift that goes in x and y, positive and negative direction in x. Of course, is always this floor that is showing the largest drift because we have the soft story here. But of course, here you have both positive and negative drift ratios because of the torque here. So it is all for this webinar. Hope you enjoyed it. And if you have a question, we have some extra minutes. This is a nice thing. It doesn't change anything because, as you have seen here, I'm using the partition database. This is the advantage of using the Python API. This one will work both on the single thread and the dual thread. So let me show you, for example, if I create a new file and I open this one is the output of the sequential OpenCs, and this one are the 4 outputs of the parallel OpenCs, okay? The script is the same because STKO takes care of going inside the database and getting the data from the correct database. So if I open the non-partition database, so the output from a sequential OpenSys, I run this one, okay, and I have the same output as before. Or I can close it. I can close this one. I can open the one of the parallel ones, okay, so I can say the second one and then it will open all the others. But STKO takes care of synchronizing the databases for you. For example, I click on the second one, but actually STKO recognizes that this one is part of a partition database, so it opens all the partitions, and I run the script, and there is actually no difference, okay? So the script is the same for one database or for many databases, okay? So for sequential and parallel, there is no difference. But this is one of the nicest things. That's why we created this kind of accessors. For example, this is the main reason why if I want the output of a certain node, I need to use, these functions. Because they seem very simple, but what they actually do is to go inside the database, try to understand where this node is, and they give me this row. This row is not an index, as I said. It's a special class that tells the displacement field where to find the correct value for that node, okay? So there is basically no difference. Is there any other question? Where could we get OpenSys? Do you recommend any guidelines for its compilation? There are some, well, actually OpenSys, just a second, so I will try to answer this one. OpenSys, I think that now it is not distributed on the OpenSys website. It was distributed before. I know that they are working on giving a new precompiled version, but for the moment you don't have a precompiled version on OpenSys, on the OpenSys website. So you can either compile it, and actually I was using a guideline that I was using for compiling OpenSys MP that works also for OpenSys SP. And I think, let me see if it is still online, but I tell you that it is not so easy. Actually, it is easier if you want to compile it on Linux machines, but on Windows it's a little bit more complicated. But if you write compiling OpenSys MP, there should be a nice completion guideline of OpenSys MP on Linux, or there was, I don't know if it is this one, there were some nice guidelines. Yes, this one. This one is pretty nice. This is quite old, so probably you need to change something. Okay, it gives you all the packages that you need and all the steps that you need to perform. I will tell you that following this line is not so easy because you need to change some of the things that are here, but they are fine to start. Okay. Otherwise, I think that there is if you go on the STKO website and you sign in, there are some instructions where to find some precompiled OpenSys SP and OpenSys MP versions, okay? If you go on the STKO website, you have a link on a non-official precompiled version of OpenSys SP and MP distributed by University of Peru, okay? So go on the website and you will find all the information on how to get OpenSys SP or MP. Okay, then can we show the calculated matrix or variable in STKO? Of course, just using the print. Okay, so when you get the data, you can just print it instead of showing it in any other form. Okay, but once you have this variable here, you can just print it and it will go here. Okay, or you can save it to a file as I did before. You can do whatever you want because once you are here, you are actually in Python. So if you do print, it goes into the STKO terminal, or you can write it to a file, or you can save it in memory. You can do whatever you want. Okay. Then we have another question here. I'm sorry, but I think I didn't understand correctly. So you have the basic code in a folder named utils that is located somewhere else, and then you can call it in the other files. But the files like drift recorded need to be in the folder in which the SCB result file. This is not necessary. Now, yes, this is the way I structured them. But let me explain you this thing. But this is not STKO specific. This is Python. Okay. In this case, the process drift plot, well, actually not this one because this one is not writing any file. But where is it? This one that writes a file, which is this one here. This one needs to be in the same folder, or actually in the folder where I want to save this file. But just because I said that when I open my file, I write drift sp STKO. So when you do not specify an absolute path, so a complete path, this one is called a relative path. And this path is relative to the current location. And the current location of a file, or actually of this file, is this folder. Okay. Now, if you want to locate this file somewhere else, like in utils, but I want to save the results in a different folder, you can specify the full path here, or you can use something called, there is another example when you want to ask the user for a folder where he wants to save the file, and you can see it here, for example, in the example of the postprocessor of the virtual results. Okay. Here, for example, I have a file that I need to get the eigenvalues. Now, instead of hard coding the location of this file, I actually ask it to the user. So I go here and I say, let me see, where is the function? It's on the top. There should be a function where I call, yeah, it's this one. QFile dialog, get open file name. Okay, get open file name basically asks the user for getting a file, okay, with this extension, and then the name of the file will be saved here. So if you want to create a script that works for everybody, not only for you, you can use the same function, but instead of get open file name, there is a function called get saved file name, and it is basically whatever you have when you do this. Okay, this is the output of a function called get saved file name. So the user specified the file, and the output will be the file that you need to save. Okay, so it's up to you. I mean, in this case, it's not STKO anymore. So the way you locate your files, it's your decision. Then coming to the same question, you said, yeah, but I'm trying, actually in this file here, I am using the utils file as a module. Now it works because the util file, even if this file is located here, okay, I can access this file because since this folder shared is stored inside the script explorer, STKO places this one into the Python search path. Okay, so when you call utils, STKO will find it because utils is inside this folder. Okay, but if I move utils on another folder and that folder is not included here, then my script will not find it. Okay, but these are some basic concepts of Python. So I will talk about them more and more again in the next webinars. Once again, UA, sorry, if we can have a workspace like MATLAB to directly copy the data, or we need to print it, or text file. Oh no, I don't have a workspace, but actually it can be a nice idea. So I will take it into consideration for future implementation. I didn't think of that, but it can be useful, yes. So having the typical MATLAB workspace where you can see the created variables, it can be nice. Actually, in MATLAB, it's pretty easy because in MATLAB, almost everything is a matrix. You have classes, but not that much. In this case, it's a little bit more complicated because we are not working with real matrices, okay? That's why probably it does not make sense because, as I said, when you create a virtual result, for example, that is not a matrix. It's only evaluated on the fly when you ask for it. Okay, so I have to understand if it is fast enough and if it makes sense to add it. Okay? But I will take it into consideration. Okay. There is any other question? All of these new files will go into the will be updated on the our website tomorrow, along with the presentation. Okay, so if there is no other question, hope you enjoyed it, and pretty much all the following webinars will be on Python. We'll show you how to do I think in the next webinar I will show how to use the Python API. Instead of using it in the postprocessor, I will use it for the preprocessor, and I will show you how to create a model in a parametric way. Okay, so instead of using the CAD command that we have here, we can actually use Python code to create a model in a parametric way. This is very useful for people doing parametric analysis of simple structures. Can we run STKO from this API from external file? Actually, you can. You need to link to a library which is inside STKO, but some of the things that are there will not work because STKO needs the application. Okay, so you can get just some subset of all the Python API that we have inside the PyMPC library. The problem is that you need STKO. You can use that library, but if you do not start an STKO instance, you will get only half of the benefits of using that library, because you can only work on the database, on a few other stuff, but of course you cannot access the application, you cannot access the document, you cannot do the 3D view. Okay, so it can be done, but we did not document it yet. Okay, so we need to document the way you can access this API from outside. The reason for this, for example, you mean you don't want to start STKO, so you don't want the GUI, you just want the API for accessing the output database, or just because you want to communicate with STKO using another software, pretty much like Grasshopper with Rhinoceros. What kind of what is the need for having the API separated from STKO? Just to understand. Okay, so just to use it without the GUI. Yes, probably what you can do is to use just the database, and probably we'll show you in a future webinar. Okay. Because not every part of the API will be useful. Okay, so some of them rely on the presence of an application. But yes, in general, it can be done. Okay. Okay, so there is no other question. I thank you everyone for joining this webinar, and see you on the next one. The next one will be on Python API for the preprocessing. Okay, so parametric modeling. Thank you everyone.